A patient recently arrived into your care from the emergency room and has an arterial and a venous blood gas drawn. The arterial gas looks okay, patient has a mild acidosis, but on the venous gas, the mixed venous oxygen saturation is 60%. Is this important? It is. This tutorial looks at the oxygen content of blood, oxygen delivery to the tissues and oxygen extraction, and explains why the hemoglobin is such an important component of this system. Fundamentals of Anesthesiology and Critical Care, with me, your host, Pat Nelligan. Understanding gases and vapors, oxygen content and delivery. In the previous tutorial, we looked at the oxygen cascade and the solubility of oxygen in plasma and interstitial fluid. I explained that the movement of oxygen from blood to the mitochondria is governed by partial pressure differences and that oxygen's low solubility is a major asset that ensures rapid transit through the tissues to the cells. But the big toe has to receive the same amount of oxygen as the arm or the brain, so a delivery system is required to carry oxygen in high concentrations to the different organs and tissues, and then dump the load efficiently and return for more. And that delivery system is hemoglobin. In this tutorial, we're going to look at oxygen content and delivery, what is hemoglobin, how hemoglobin carries oxygen, how to calculate oxygen content, how to calculate oxygen delivery and uptake, and what happens with blood loss and crystalloid resuscitation. Let's start with hemoglobin and extracellular proteins. These are sometimes known as plasma proteins, but they're also present in the interstitium. Hemoglobin is measured in grams per deciliter, that's grams per 100 mils, and the normal hemoglobin is between 12 and 16 grams per deciliter, or 120 to 160 grams per litre. The serum albumin is recorded in either grams per litre or grams per deciliter, so the normal albumin is 42 to 45 grams per litre, or 4.2 to 4.5 grams per deciliter. You'll often encounter the term hematocrit in your clinical practice. The hematocrit is how much of the blood volume is occupied by red blood cells expressed as a percentage. So it's the volume percent. For example, a hematocrit of 45% means that 45 mils of red blood cells are present in 100 mils of blood. In other words, 100 mils of blood is made up of 45% red cell mass, and the hemoglobin is usually 1/3 of the hematocrit. The rest is made up of the remainder of the red blood cell, the membrane, the structural components, and water. White blood cells and platelets represent approximately 1% of blood mass. Approximately 22% of blood mass is made up of protein. Of that, about 70% is derived from hemoglobin, and the remainder come from plasma proteins, approximately twice as much albumin as globulin. So as a simple rule of thumb, 70% hemoglobin, 20% albumin, 10% globulin. Remember that the albumin and the globulin are in the plasma. The hemoglobin is inside the red cell, so that's an intracellular protein. The others are extracellular proteins. There is 8.5 times as much protein in the blood as there is in the interstitial fluid, and 2.5 times as much so-called plasma proteins in the plasma as in the interstitial fluid. The main role of hemoglobin is to bind oxygen, and it's a complex arrangement where oxygen binds reversibly to the protein that's known as heme superstructure associated with an iron molecule in the ferrous state. The iron molecule holds oxygen in a coordinate bond, a loose connection stabilized by the protein. The heme part specifically refers to the iron-containing porphyrin group. The globin refers to the protein part. It's the metal component that binds the ligand. This is a cartoon to represent hemoglobin and its oxygen binding sites. We are starting with a situation that never happens in physiology, a hemoglobin particle that has no oxygen bound to it. We will call this deoxyhemoglobin, but it is really anoxyhemoglobin. There are 4 binding sites for oxygen on a hemoglobin molecule. As oxygen binds to hemoglobin, the strength of that bind becomes progressively stronger. So the 4th molecule that attaches to hemoglobin is bound tighter than the first. Each hemoglobin molecule binds 4 oxygen molecules. How much oxygen does 1 gram of hemoglobin carry in mils? This can be calculated, but I will warn you that the number that we're going to calculate is slightly different from the number that is quoted in all of the literature. This is a derived variable. The stuff in the literature has been derived from in vivo studies. So we're going to start with the molecular mass of hemoglobin, and that's 64,500 grams per mole. Each hemoglobin molecule binds 4 molecules of oxygen. So 1 mole of hemoglobin binds 4 moles of oxygen. The molar volume of oxygen at standard temperature and pressure is calculated as 1 mole equals 22.4 liters. So we can calculate out the volume of oxygen bound per mole of hemoglobin, and this is really simple because it's 4 times 22.4 liters. So 1 mole of hemoglobin binds 89,600 mils of oxygen. If we divide that by the molar mass of hemoglobin, it's 89,600 divided by 64,500, and that works out at 1.39 mils of oxygen per gram of hemoglobin. This figure is known as Höfner's constant, and the 1.39 mils that we calculated is the ideal quantity of oxygen that binds hemoglobin. That never happens. And after several decades of in vivo research, everybody agreed and now accepts a lower number of 1.34 times the hemoglobin in mils per gram. Why is this the case? Well, the speculation is that not all hemoglobin is able to bind oxygen. There may be abnormal hemoglobin present, such as methemoglobin or carboxyhemoglobin. There's some physiological shunt, and there are changes in the oxyhemoglobin dissociation curve, etc. So this is the number I want you to remember, and it leads neatly to us now exploring one of the key calculations in all of medicine, and this is core knowledge. This is the calculation for the oxygen content of 100 mils or 1 deciliter of blood, and it is 1.34 times the hemoglobin times the saturation over 100 plus the PaO2 times the solubility coefficient. There are 2 parts to this. 1.34 times the hemoglobin times the saturation divided by 100 refers to the oxygen bound to hemoglobin. The reason why you multiply it by the saturation is because the entire content depends on how saturated hemoglobin is. If the hemoglobin is 100% saturated, the multiplier is 1. If it's 90% saturated, the multiplier is 0.9. The second component of the calculation is far more modest. And we dealt with this in the previous tutorial, and that's the component of oxygen that's in the blood that is dissolved. And that is the PaO2 multiplied by the solubility coefficient. And the solubility coefficient, as we saw before, is in either kilopascals or in millimeters of mercury. You will note that the solubility coefficients in this table are in mils per deciliter, not mils per liter, to match the conventional way that we measure hemoglobin. So be very careful of your decimal points when making calculations. Now let's look at some of these components in a little bit more detail. What is the impact of a change in the saturation on oxygen content? Remembering that 1 gram of hemoglobin binds 1.34 mils of oxygen if fully saturated. If the saturation is less than 100%, for example 97%, the actual oxygen content bound to hemoglobin will be proportionally less. So if the hemoglobin is 15 grams and it's fully saturated, then 15 times 1.34 times 1 equals 20.1 mils of oxygen per 100 mils of blood plus whatever has been dissolved. If the hemoglobin of 15 grams is 92% saturated, then the calculation is 15 times 1.34 times 0.92, and then the result is 18.5 mils of oxygen per 100 mils of blood plus the dissolved oxygen tension. So any reduction in the saturation has a direct proportional impact on the oxyhemoglobin content of blood, and that can be quite devastating. So if a patient goes from, for example, 100% to 85%, there is a dramatic fall in the oxygen content in blood, and it's higher than you might imagine, as we will discuss in the next tutorial. So we can now calculate the entire oxygen content of arterial blood by calculating out our oxyhemoglobin content plus our dissolved oxygen content. And we've done this before. 0.023 times 12 kilopascals or 0.003 times 90 will give us 0.28 mils of oxygen per deciliter per 100 mils of blood. So we can add 20.1 and 0.28, and that will give us 20.3 mils per deciliter or 203 mils of oxygen per liter of arterial blood. Sometimes in our clinical practice, we encounter patients who are chronically anemic. For example, a patient who has a hemoglobin of 8 grams per deciliter with normal blood volume will have more or less the same amount of oxygen dissolved in their plasma, maybe a little bit more because there is a slightly higher plasma volume. But the hemoglobin at 8 grams per deciliter that is fully saturated, when you do the calculation, and maybe you should just pause the video now and do the calculation, that has a hemoglobin content of 10.7 mils per deciliter, approximately 11 mils. That's a little more than half of the oxygen content of the same patient if they had a hemoglobin of 15. But why doesn't this patient develop hypoxia? There are 3 reasons. The first is that there is plenty of reserve in the system. The second is the way that oxygen binds to hemoglobin. It changes, and we'll discuss that when we talk about oxyhemoglobin dissociation curves. And the third is that the cardiac output increases to maintain oxygen delivery. Oxygen delivery is usually represented by DO2, the little dot over the D. And it's the cardiac output times the oxygen content. The normal cardiac output in this setting is about 5 litres, 75 mils of stroke volume times 80 beats. And we already found that in the normal patient, the oxygen content was 203 mils per litre. So we can multiply these out. 5 litres of cardiac output times 203 gives an oxygen delivery of 1,015 mils per minute. Our anemic patient's cardiac output is actually 8 litres, and that's 80 mils, a slight increase in the stroke volume, but a dramatic increase in the heart rate to 100. And 8 times 110 mils is 880 mils per minute. So the DO2 is the cardiac output times the oxygen content. And again, this is a core knowledge calculation. With this knowledge, we can now move on and look at oxygen consumption, and that is marked by VO2, V with the dot over it, O2. And it's derived by calculating out the arterial and venous oxygen content and multiplying the difference by the cardiac output. This is the Fick equation. The VO2 is the cardiac output, sometimes represented by a Q with a dot over it, times the arterial minus the venous oxygen content in mils of oxygen per minute. Calculating venous oxygen content, CVO2, is really easy because we can do a venous blood gas, and this will measure the mixed venous oxygen saturation and the partial pressure of oxygen in venous blood, and we can substitute the numbers into our calculation so that it's the SVO2 rather than the SaO2, and it's the PVO2 rather than the PaO2. So if the hemoglobin is 15 and the SVO2 is 70%, the hemoglobin oxygen content is 15 times 1.34 times 0.7, or 15 mils per deciliter. The dissolved oxygen content is 5.3 kilopascals, or 40 millimeters of mercury. It's 0.023 times 5.3 in kilopascals, or 0.003 times 40 in millimeters of mercury, and that works out at 0.122 mils per deciliter. Adding the two together, we get 15.1 mils per deciliter, or 151.2 mils of oxygen per liter in venous blood. The arterial to venous oxygen content difference is about 5 mils per deciliter, or 50 mils per liter. So we now know that our arterial oxygen content is 203 mils per liter, our venous oxygen content is 151.3 mils per liter, and the AVO2 difference is 51.7. When we multiply this by the cardiac output of 5 liters, that works out at 258 mils of oxygen consumed per minute. And that tallies with what you've always been told, that we consume about 250 mils of oxygen per minute. But from this, we can also calculate out the carbon dioxide production, because in a normal diet, we produce 4 mils of carbon dioxide per 5 mils of oxygen consumed. We call this the respiratory quotient, and the respiratory quotient for a balanced diet is normally 0.8. So if we multiply the respiratory quotient by the oxygen consumption, then we can come up with the amount of carbon dioxide that's produced per minute, and that's 258.5 times 0.8, or 206.8 mils of carbon dioxide produced per minute. As a quick aside, if a patient becomes apneic, how much oxygen is stored in the body? In this table, I have two major columns. One is the volume of oxygen stored in room air. The second is the volume of oxygen stored if the patient has been pre-oxygenated with 100% oxygen. And so we have oxygen as gas in the lungs. That's functional residual capacity. That's the amount of air that's in the lungs at the end of a normal tidal volume. The oxygen that's bound to hemoglobin, although not all of that is available. The oxygen that's bound to myoglobin, dissolved in extracellular fluid, dissolved in interstitial space, and the total oxygen storage. And my calculation is that there is just shy of about 1,600 mils of oxygen stored in the body if everything just stops right now. But of course, everything doesn't stop. If you give a patient 100% oxygen, then the total oxygen content of the body just statically will increase quite dramatically up to 3.8 liters, and a significant proportion of this is in the functional residual capacity of the lungs. And that's important, and that's why we give patients 100% oxygen if we're worried about them becoming hypoxic during induction of anesthesia or intubation for any reason. Keep in mind that we're consuming 250 mils of oxygen per minute, and that total oxygen storage is not available. So in general, there is about 3 minutes where a patient may become apneic before they start becoming hypoxic if they're breathing air. That can be prolonged quite substantially up to 10 or 11 minutes if they've been breathing 100% oxygen. Let's move on to look at oxygen delivery associated with blood loss. This is our patient who has a hemoglobin of 15 grams per deciliter with an oxygen content of 20.3 mils per 100 mils, a saturation of 100%, a blood volume of 5 liters with a venous oxygen content of 15.1 mils per 100 mils, and 250 mils are extracted per minute. The cardiac output is 5 litres, 75 mils stroke volume, 80 beats per minute, giving oxygen delivery of just over 1 litre, 10-15 mils per minute. The mixed venous oxygen saturation is 75%. Now our patient loses 2 litres of blood, so the blood volume drops to 3 litres. The saturation is exactly the same. Because the patient hasn't been in any way resuscitated, the hemoglobin will stay the same. And that means that the oxygen content per 100 mils is still 20.3 mils per 100 mils. The patient will compensate for this loss of blood volume by increasing cardiac output from where you would think it would be to where it actually is. So the stroke volume falls associated with the blood loss, but the heart rate goes up, and the cardiac output in this situation is 4 litres. 250 mils of oxygen are extracted. The oxygen delivery is about 800 mils per minute, so it hasn't fallen all that dramatically because of the compensation associated with the increased cardiac output. But there is a substantial increase in the amount of oxygen that's being extracted per unit blood. And as a consequence, the venous oxygen content falls and the mixed venous oxygen saturation is 60%. That's why it's really important to measure mixed venous saturation in patients who are bleeding or involved in trauma. It is a really good indicator of blood loss, of volume loss. A mixed venous saturation of 60% or lower means substantial volume depletion. Often in these patients, the blood pressure actually looks okay. The patient looks okay. They may have a tachycardia. Even the lactate may not be that high, but the mixed venous oxygen saturation tells a different story. From the early 80s to the mid-2000s, there was a swing towards giving patients crystalloid, particularly at the site of a trauma, to start the resuscitation. Thankfully, that has gone a bit out of fashion now. But let's look at what happens if we restore this patient's circulating volume with crystalloid. So we're starting off with a blood volume of 3 litres, and we're going to give the patient several litres of crystalloid to get the blood volume up to 5 litres. Now the hemoglobin has dropped to 8 grams per deciliter because we've just given clear fluid. So we've expanded the plasma volume, but we've diluted the hemoglobin in the process. So the oxygen content of blood now is 10.7 mils per 100 mils. The saturation is the same. Oxygen consumption remains 250 mils. The cardiac output is 5 litres, but the oxygen delivery is 235 mils per minute with the same oxygen consumption. And as a consequence, the venous oxygen content falls, as does the SVO2. It's lower than before. Now, these numbers are all estimates, but you can see that although cardiac output is restored and the heart rate slows down, the actual oxygen delivery falls. In addition, due to reversal of vasoconstriction and increased tissue perfusion, oxygen consumption may increase at this stage. The learning point here is that if there is significant blood loss, the treatment is blood products, not crystalloid. Let's review this tutorial. This was a tutorial about oxygen content and delivery. I explained what hemoglobin is, how hemoglobin carries oxygen, how to calculate oxygen content, how to calculate oxygen delivery and uptake, and what happens with blood loss and with crystalloid resuscitation. Next time, we're going to look at the oxyhemoglobin dissociation curve. I'll see you then, and I guarantee you'll learn something.